Welcome to the deep dive. Today, we're getting into something pretty foundational, how computers actually understand shape. We're talking vector and point data structures in design.
Yeah, it's core stuff. We've got material here from a computational design workshop, some videos, some notes, English and Korean, looking at how digital tools handle forms.
Exactly. And our mission really is to pull out the key ideas about vectors and points, why they're so crucial for design, and how they pop up in different software.
It's the groundwork,
Yeah.
useful whether you're deep into coding or just curious about how digital design actually works.
Okay, let's unpack this.
So everything you see, all the digital geometry in design software, it really boils down to two kind of simple ideas: points and vectors.
Right. Points first.
Yeah. A point is basically just a location.
Yeah.
In 3D space, it's defined by three numbers: X, Y, and Z coordinates. Just picture like a single spot floating there.
A specific address. Got it. In this digital 3D world. And vectors also use X, Y, Z, but they mean something else.
Exactly. A vector isn't where something is, it's direction and magnitude. How far in which way.
Ah, okay.
Think of it like an arrow, showing you how to get from one spot to another. The XYZ numbers tell you how much to move along each axis, and the arrow's length is the magnitude, the distance.
So a point is I'm here, and a vector is go this way, this far.
You got it. That's the fundamental difference.
And these two things, points and vectors, they're really the absolute building blocks for all the complex shapes we see digitally.
Absolutely. The source material puts it clearly. Vector and point data structures
Yeah.
are essential for controlling and manipulating most shapes. Without them, the computer just wouldn't have a way to, grasp or work with geometry.
Okay, foundation laid. Points are locations, vectors are directions and distances. Now, what can designers actually do with these vectors?
Right.
The workshop gets into operations, right?
That's where it gets practical. The workshop covers the main things you do with vectors: addition, subtraction, scaling, and normalization.
Addition, subtraction, scaling. Makes sense. Normalization sounds a bit more technical, maybe?
It does, yeah, but the idea is pretty straightforward when you break it down. Let's start with adding vectors.
Okay.
When you add two vectors, you're basically sticking them end to end. Imagine one arrow, then start the second arrow where the first one finishes.
Right.
The sum, the result, is the single arrow that goes from the very start of the first one to the very end of the second one.
Okay, so like combining movements. Move this way, then move that way. The total move is the sum.
Exactly. It could be forces acting together or just shifting an object step by step.
Makes sense. And subtraction.
Subtraction is often about finding the vector between 2 points. If you have point A and point B, the vector you get from B minus A points directly from A to B, and its length is the distance between them.
Okay, so it tells you the relationship direction and distance between two spots. Useful.
Very useful for figuring out how things are arranged in your design space.
And scaling. That sounds like just changing the length.
Pretty much. You multiply the vector by a regular number, a scalar.
Yeah.
Bigger than 1 makes it longer, between 0 and 1 makes it shorter.
Right.
And if you multiply by a negative number, it flicks the direction too.
Yeah.
So you can resize things or change the intensity of something represented by a vector, like a force.
Got it. More force, bigger vector. Less force, smaller vector. Okay, now normalization. What's that about again?
Normalization is taking any vector, no matter its length, and shrinking or stretching it so its length becomes exactly 1.
One. Why?
One, because you keep the direction the same. You're throwing away the how far information and just keeping the which way. It becomes what's called a unit vector.
A unit vector. So pure direction.
Exactly, pure direction.
Yeah.
Really handy when you just need to know orientation, like which way a surface is facing,
Right.
without worrying about size or scale.
Right, like setting a direction for something to move, but not how fast. Okay, that's actually a really neat concept.
It is. And the key takeaway here is that even when you use fancy tools in your software, underneath it all, the computer is doing these basic math operations on the vector components.
Now, the workshop materials, they show this stuff happening in like a whole bunch of different places, right? Processing, web stuff with JavaScript, Rhino and Grasshopper, even C# and Python.
Yeah, it's a good survey. And what's really important, what the sources emphasize, is that the math itself doesn't change. The same underlying mathematical concepts apply across different programming environments. That's a direct quote.
So even if the code looks totally different, maybe clicking blocks in Grasshopper versus typing lines in Python, the computer's doing the same core vector addition calculation.
Precisely. The way you tell the computer to do it changes, the syntax, but the fundamental x plus xy plus y, z plus z logic stays the same. The workshop even shows, I think it was C-sharp, how you might use a simple plus symbol if the library supports it, or you might have to add each component manually. Same result, different ways of writing it.
Which leads into APIs, right? Application programming interfaces. These sound like they hide some of that complexity. The instructor mentions RhinoCommon.
Yeah, APIs are basically toolkits. Collections of pre-made functions that handle a lot of the low-level stuff for you, so you don't have to code the distance formula from scratch every single time, for instance.
Right. Shortcuts.
Exactly. The instructor even jokes about it. API is super simple, right? I just call this line, and it's good to chew, up to chew. Makes it seem effortless.
Huh. Okay. So they're convenient. But there's a catch, I'm guessing.
Well, not a catch exactly, but a strong recommendation. The workshop stresses that while APIs are great, understanding the math that the API is doing for you gives you way more power.
How so? If the API works, why worry about the gears turning inside?
Because knowing the math helps you debug when things go wrong. It lets you figure out why your result looks weird. It also means you can maybe create custom solutions if the standard API function doesn't do exactly what you need.
Okay. More control, better troubleshooting.
And potentially more creativity, because you're not just limited to the pre-packaged tools. You understand the ingredients, so you can cook up something new. The instructor really pushes this. Understand the formulas, even for simple things like distance. Know what's happening under the hood.
Like knowing how your car engine works, even if you usually just turn the key. Good analogy. Okay, something else mentioned was coordinate systems. That can feel a bit abstract sometimes.
Yeah, they're like the background grids the computer uses to make sense of space.
Right.
The most common one we all know is Cartesian XYZ axis right angles.
Right.
But there are others, like spherical coordinates, think latitude, longitude, radius, or cylindrical coordinates. The key is that the same numbers, like 5, 3, 2, could mean a totally different spot depending on which system you're using.
So it's like different map projections. Same globe, different ways of drawing the map, and you need to know which map you're looking at.
That's a great way to put it. And understanding these systems and how to convert between them is important, especially when you move data between different software or trying to represent real-world locations. The instructor's analogy was giving directions using street names versus using compass directions, different systems, same goal.
Okay, that makes sense. Space isn't just empty, it has these defined frameworks. Now, the materials also talked about planes, but not just like flat things.
Right. In this computational context, a plane isn't just an infinite flat sheet. It's usually defined by a specific point, its origin, and then 3 vectors representing its local x, y, and z axis.
Local axis, so like a little coordinate system attached to that plane.
Exactly. Think of it like a portable mini-grid you can place anywhere and orient however you want in the main 3D space. The workshop mentions sometimes even a single point can be treated as a default plane by software.
Why is that useful, having these local coordinate systems?
Super useful for positioning and orienting objects relative to each other, or relative to a specific surface or area within your design. It simplifies things. You can work within that plane's local system. The instructor kind of sums it up as a plane being a collection of vectors and an origin point working together.
Got it. Local context for objects. Now, near the end of one clip, matrices were mentioned briefly. Transformation matrices. Sounds mathematical.
It is a bit more advanced, yeah. But matrices are a really efficient way to bundle transformations together. Things like moving an object, rotating it, scaling it. You can represent all those actions in one single matrix.
So instead of doing move, then rotate, then scale as separate steps.
You apply one matrix, and it does all of them at once to all the points defining your object. It's very efficient computationally.
And this is happening behind the scenes in our software, usually.
Often, yes. The workshop points out you might not directly manipulate matrices as a beginner, but knowing they exist and what they do combining transformations is good background knowledge for when you tackle more complex stuff later on. It helps understand how the software achieves complex manipulations so smoothly.
Okay, so bring it all back. We have points, vectors, operations on vectors, different coordinate systems, planes as local systems, matrices for transformations. Why is really getting this fundamental vector and point stuff so important for designers?
Because, as the workshop really drives home, the goal is often to go beyond just using the pre-built tools. It's about being able to translate your design ideas into instructions the computer understands, to code the thought, as they put it.
Code the thought. I like that.
And vectors and points are the absolute basic language for that. The sources call it the grammar of data in design. If you don't understand the basic grammar, you can't really form complex or novel sentences, right?
Makes perfect sense. You need the nouns and verbs before you can write poetry.
Exactly. And understand this foundation lets you build up to more complex things like curves and surfaces, which are often defined using points and vectors. The instructor points out this connection, understand polylines, then you can understand NURBS curves. It all builds.
So it's not just theoretical, it directly enables more advanced creation.
Absolutely. The workshop even had an assignment focused on actually coding these vector operations and visualizing them, making it
Oh,
tangible, connecting the math to the visual output.
All right. So the next time you, our listener, see a really complex 3D model or some kind of dynamic digital installation, maybe take a second to remember that underneath it all, it boils down to these fundamental pieces. Points locating things in space and vectors defining the relationships and movements between them. What kind of new design possibilities does that awareness unlock for you?
Hmm. That's a great question to leave people with.
Thanks for taking this deep dive with us today.